Hi there, we're going to talk about modular multiplicative inverses now. So this is going to be helpful for starting to work and solve equations in the modular world. So we touched on this earlier a little bit, and now we're going to go a little bit further with it. Okay. So let's start off with the question. Find the multiplicative inverse of 13 bar in Z15 or mod 15 if it exists. So that's the question. We've got to figure out, does this even exist? So let's think about what this looks like. So what we're essentially saying is 13 bar x equals 1 in mod 15. Okay, that's what we're essentially trying to solve, is that particular equation. Well, if we think about this, we can take this into the world of integers, and we'll talk. We can take this into the world of integers by remembering that mod 15 just means that 1 is the remainder plus some multiple of 15. So I can rewrite this as 13x equals 1 plus 15y. Okay. If you're ever stuck, you can always return to the world of ordinary integers and work on it there. It's a little more powerful to stay in the mod world, but that's definitely where we would like to go, is to be able to work in mod all the time. But ordinary integers can be helpful. And in particular, because this one, if I look at this equation, I can subtract 15y, and I get 13x minus 15y equals 1, and since we know that x and y have to be integers, we've got a linear Diophantine equation here. So we've done this before. We know how to do this. We know how to solve this particular equation. So what do? Well, we could certainly go through the royal road. The question is, does it have a solution? Well, we know that the GCD of 13 and 15 is 1. So yeah, we know that actually guarantees that we are going to have an integer solution to this particular equation. So that's great. We know then we've now established the fact, does it exist? Okay. So we've answered the second part of that question, if it exists. Interestingly enough, one thing to kind of think about is that if the modulus is actually a prime number, like Z13, Z19, and various other prime numbers, it turns out all of the numbers in that system have a multiplicative inverse, except for 0, of course. So that's kind of nice. And that's mainly, it comes down to this statement right here, because what we're essentially saying then, so 15 is our mod here. Well, if that were a prime number, then everything is going to be relatively prime to a prime number. So that's why that works. So that's the nice thing. And again, that we wouldn't have to go back into the ordinary integers to know if it exists if we knew that it was z sub some prime number. Okay. So anyways, if this were a bigger set of numbers, we could do the royal road problem. I'll let you, if you want to figure this out. But I do know that, for instance, when I look at this, if I multiply x times 6, I'm going to get like 91. But 6 times 15 is 90, so that's what I'm looking for. So I have x equals 7 and y equals 6. Okay. Now, what that, however, means, like, I don't really need the y equals 6. Okay. Because that was just to help us solve the problem. What we really wanted is we wanted the x. So what this allows us to say then is that the multiplicative inverse is 13 bar is 7 bar. Okay. As kind of a counterpoint to that, what about the case where if we want to find the multiplicative inverse of 6 bar in z sub 15, if it exists? I'm just going to shift that up. Well, we would basically do all of the same things again. So I'm going to start off with 6 bar times x equals 1 bar. and this is in mod 15. So again, we can turn this into the ordinary integer. So we get 6x plus, sorry, not plus, 6x equals 1 plus 15y. And then that gives us 6x minus 15y. And if you remember your work from Diophantine equations, the GCD of 6 and 15 is not 1. So there's no solution to this. There's no integer solution. They have a common factor of 3, so not going to work. So we can't do it. So the answer here is no, does not exist, which is good to know. And could we extrapolate a little bit more about that as to how we'll know it's not without getting to this point? Well, yeah, we look at the bar, the 6 and the 15, and we ask what's their relationship. If they're relatively prime, then we know there's a multiplicative inverse. If they're not relatively prime, we end up with a situation like this, and there's no multiplicative inverse. So that's something to keep in mind. So what do we do with this? Well, let's. One thing we can do with this now is we can start solving some equations. So let's consider the equation. We want to solve 13 bar times x. I keep putting equals. Let's see. Plus 4 bar equals 1 bar. Okay. So we want to solve that particular equation. Well, first step, just like algebra 1, I'm going to subtract the 4 bar from both sides because we know we can do that with these numbers and it stays the same. So if I subtract 4 bar, I get 13 bar x equals negative 3 bar. And again, this is all, I'm going to just go ahead and put the mod 15 here so we remember. I could go ahead and change the negative 3 bar to 12. It really doesn't actually matter. But I'm going to just leave it for negative 3 right now because we know they're equivalent. Negative 3 bar and 12 bar are the same thing. But here's the nice part is I can go ahead and multiply both sides by the multiplicative inverse. So I would have 7 bar, and we'll put another 7 bar here. And let's come back. So then we have our 13 bar x and our negative 3 bar. Okay. On the left-hand side, well, the whole point of finding 7 bar was it was the multiplicative inverse of 13. So therefore, that's just 1. So 1 bar or 1 times x is just x. On the right-hand side, using the property from that we looked at in a previous video, I can just multiply 7 times negative 3, and I get negative 21 bar, which is an acceptable answer, but if we bring it back to the remainders of 15, the modulus 15, then this comes out to be 9 bar. And so the solution to this particular equation is 9 bar. Notice we never left the modular world this time. We didn't have to pull in the equation of ordinary integers. So I hope that helps make some sense of multiplicative inverses.